today's topic is signals and system review for the material that we are going to study after the midterm, which is frequency modulation. I'm sure we can finish it in under 1 hour, then you guys can go study for the exam. Okay, so there are an assortment of topics, and the first one is what is the bandwidth if the bandwidth of m of t is b. What is the bandwidth of m square b? What is the bandwidth of m cube b? So if it's better to approach this intuitively, because if you think about it intuitively, it's very simple. So take message, something like an audio waveform. It has frequencies from like 50 hertz to say 15 kilohertz. Take one of those waveform, one of those cosine waves, cosine omega t, and when you square it, it becomes cos square omega t, and cos square omega t is actually 1/2 1 plus cos 2 omega t. You guys know this formula. Cos square x is 1 plus cos 2x and half. So you can see the frequency doubles. And some of you may say, okay, but there is also another frequency, and m of t is this plus cosine, say omega 1t plus cos omega 2t, and you are looking at the whole thing squared. So then what happens is the middle term is going to be cos a times cos b, which is cos a plus b and a minus b. And a plus b will never go higher than a square or b square, whichever is the highest. So essentially we can actually make this more rigorous, but don't really waste your time on it. But basically the conclusion is bandwidth of m square is twice the bandwidth of mt. So please remember this. Bandwidth of m square is 2 times the bandwidth of m of t. The bandwidth of m cube is 3 times the bandwidth of m. So basically the theorem is m to the n has, or I should change this, m to the nt has n times the bandwidth of m of t. That's it. That's the first theorem. Okay, so that's what this is. The second theorem is differentiation or integration do not change the bandwidth. So for example, suppose we have a message signal and its bandwidth is capital M. Now, if you look at the properties of the Fourier transform table, you will realize when you differentiate, in order to get the new Fourier transform, what you do is you take this and multiply by 2 pi j f. 2 pi j f. Okay, here I have changed it to omega. You guys know omega is 2 pi f. So in the table you will see multiply by 2 pi j f, or 2 pi f j, or j 2 pi f, j 2 pi f. Okay, so if you look at this expression, it is the same amplitude response, and what this does is it changes the phase angle. So in other words, amplitude of the bandwidth, amplitude of the Fourier transform does not change. It is still the same, because the amplitude of if you write this in the polar form, you will realize this part goes into e to the something. So the amplitude of this. So okay. So the conclusion is there is a big theorem that differentiation does not change the bandwidth. Integration also does not change the bandwidth, because we are going in the other way around. Okay. All right. And now here, I hope you remember this from the first year, because we also need this for FM. Okay. fundamental theorem of calculus. So basically, if you have a number here and a variable here and a different variable here, how do you differentiate this with respect to this one? So the answer is simply you take this and replace with x, but let's focus a little bit on it, how it came from, where does it came from. If you look at this, this is actually the area under the f function on the t-axis. So the horizontal axis is t, but you are taking the area from t equals a to x. So in other words, you have a curve, the horizontal axis, the vertical axis at a, but the vertical line at a. The second line is moving x because t is x. What is this moving area? That moving area is here, given as this integral. Remember, so t is equal to a is fixed, t is equal to x is, when x varies, it varies, goes like this. But the curve is on top. So that area is a function of x because a is fixed. And this is, we have calculated the area. Or you can think of as this integration is performed and you are subbing in a and x. So this is a function of x. So if you differentiate x, this function, g prime x is simply f of x. So what you do is you take this x and plug it in here. That's it. You don't differentiate f. Okay. So this theorem comes in calculus just before you learn how to do definite integrals, like find the antiderivatives and plug it in. The proof of that comes from this. And so here is an example. So all you guys need to know is how to do these examples, okay? Because we are going to apply fundamental theorem of calculus in this fashion. So consider this example. G of x is a to x cosine t dt. Then g prime t is just for t put x. That's it, cosine x. If it is square root of t, then it is, and here instead of x I put u, so this is g of u. So g prime u is square root of u. If g of t is a to the t 1 over 1 plus x squared dx, then g prime t is 1 over 1 plus t squared. You just put t here for x. Okay. And then this is basically the same theorem. Here I have given you the condition, and now here is an example from this course. When we do FM, you will encounter this. So g of t is given as omega psi t plus minus infinity t this, and you need to find g prime t. So the derivative of this is omega c, and the derivative of this m at t. And you are probably wondering, this is not a constant, it is negative infinity. Is that okay? Yes, it doesn't have to be any constant. It can be any number. It doesn't matter if it is negative infinity. Alright guys, so that is the easy part. Now I'm going to skip this because this part is a little bit complicated. So I'm going to go to the next section, then I will come back. Okay. We know the spectrum of dSPSB, which is mt times cosine omega ct, is twice the it is shifted to fc and negative c, but the spectrum is basically capital MF. So if you multiply by this cosine omega ct, basically the new spectrum is the spectrum of M shifted to fc and negative fc. We are just going to prove, instead of multiplying by cosine, which is what we do in dSPSB or when we analyze it, if we multiply by sine, the result, the spectrum is this. And what is the difference? Again, it is shifted to fc and negative fc, omega c and negative omega c. Half is there, exactly the same result, but there is a phase angle, e to the something. So in other words, the spectrum of mt sin omega ct is the spectrum of mt shifted to fc and negative c, but then rotated in phase. So if you are worried about the amplitude spectrum only, then the spectrum is exactly the same. Okay, because this is the phase angle. Okay, so amplitude spectrum is exactly the same as ds/PSP when you multiply it by this. And another conclusion is, so we know, so this this is half, right? Half. The spectrum of M goes here and here. So you are going to use this later in the FM, that you are going to see, you will see some expression like ds/PSP, what, but instead of cosine you will see sine. Now we know that a spectrum of ds/PSP is the bandwidth is 2b, 2 capital B, where B is the bandwidth of the message signal. So in FM it's more complicated, the bandwidth. However, one part FM bandwidth will be given as this plus that plus this. One of them you will see it's actually this expression. So to calculate the bandwidth of this, you will say it is twice the bandwidth of m of t. And the derivation is here. I don't want you to look at the derivation today. You can look at it after the midterm for your peace of mind. But I'm not going to ask you this in the final exam, this derivation. Okay, as long as you remember the spectrum is given by this expression, or amplitude spectrum is the same as the ds/PSP. Basically the message signal spectrum shifted to FC and negative FC, that's fine, and half. Okay, remember the half. Alright, that's fine. So don't spend your time tonight going through this derivation. It's not that important. Just review this before I start teaching FM. Okay, one more thing I have to tell you, FM is going to get really involved. There will be a lot of slightly more complicated math, but I will explain everything, and there will be plenty of numerical examples in the exam. You just have to do the numerical examples. Even though there is complicated math, I am not going to ask you to derive any complicated math in FM in the exam. Okay, final exam. All right. Section 4 and 5. I strongly urge you to read that section after the midterm, before my lecture on FM, because this part is a little bit complicated. Actually, not the next first lecture after the midterm, probably the lecture after that. So in other words, second lecture after the midterm. All right. Again, this is very complicated business. However, well, I am going to explain it, but after you explain, what is expected of you is this. The FM's bandwidth, when it is tone modulated, remember we had just m of t for AM, but we also studied tone modulation. A single cosine waveform modulates your carrier. So in FM also we will study two cases, general FM and then tone modulated FM. When we do tone modulated FM, when we calculate the bandwidth, we will get an expression, and that expression will involve this function. Okay, this is called Bessel's function of the first kind. You will see the English in a while. Bessel's function of the first kind, and we will give you this table. In order to calculate the bandwidth, what you have to do is the calculations will involve from the question you will know what is n and beta, and you choose one of these values. In other words, when you calculate the bandwidth, you may have to look at a number that is Bessel's function where n is 2 and beta is 1. So if n is 2, which is here, and beta is 1, the value of the Bessel function is 0.11. So after I explain all of this, all you need to know is how to use the Bessel table. That's it. If you know the n value and beta value, go to the corresponding n values are given in the row, beta values are given in the columns. See here 2. So if beta is 5, you will go to this column. Beta is 0.5, you go to this column. N is 2, you go to this row. That's it. That's the end result. But now I am going to explain what is going on. Where does Bessel's function of first kind came from? Okay, that part is slightly complicated. Okay. So Bessel was an astronomer, but he is also interested in math. So he was trying to solve a particular problem in classical mechanics, which is Newtonian mechanics. I believe it is the three-body problem. Maybe you guys have heard about it. And when he wrote the Newton's equation for that bodies going around a planet, he ended up with a differential equation, and it's not easy to solve that differential equation. It turns out it is a second order differential equation. So there are two solutions. I'm sure you guys studied differential equations. There were two solutions, but the solutions cannot be written in closed form, meaning you cannot, the answers came as an integral, but the integral cannot be, they didn't have an antiderivative, the function inside. So the only solution way to write the solution is as an infinite series. So this is a second order differential equation. So there are two solutions, two infinite series. The first one is called Bessel's function of the first kind. Second one is called Bessel function of the second kind. Now to see what are these infinite series, another famous example is the area under the normal distribution. Area under the bell curve, because e to the minus x squared does not have an antiderivative. So you can only write it as a infinite series. But whenever the solution is in an infinite series, people give the results in a table. So normal distribution, area under the normal distribution can be obtained in table. Usually it is in one of your statistics books. Statistics books have the area under the normal curve at the back of the book. So you can calculate those probabilities and confidence intervals and so on. 90% confidence and 95% confidence interval and so on. So just like that, Bessel's functions are calculated using the table, and I already explained. All right. Now this is how Bessel's function of the first kind and nth order. So this is called the first. Anyway, we are only interested in the first kind. The second kind give you the other solution. We are not interested in that. So it is written j sub n at beta. N is called the order. And then this is that complicated integral. It has n in it and beta in it. So it is this integral that is the solution, but there is no antiderivative for this. Okay, so because look at this, this is sine x minus x, e to the sine x minus x dx. We probably don't even have an antiderivative for e to the sine x. E to the sine x cannot, there is no antiderivative. How are we going to do e to the sine x minus x? Okay, that's why the result of this is an infinite series, or you can look up at a table. So if you want to find j2, 3, j sub 2 at 3, you have to go to that table I mentioned. Okay. Now, we are not going to write any of this in the exam or even in the lecture notes. Sorry, no, I have to explain this. So, when we derive the FM bandwidth, tone modulated FM bandwidth, we are going to end up like an expression similar to this. Okay. But I will explain essentially what happens. Okay. Okay. So now please forget about Bessel functions. This is the next section. I'm going to explain this and two will be connected, but you have to temporarily forget about it. I want you to think about, so when we calculate the bandwidth of FM bandwidth, tone modulated bandwidth, we will encounter this new function. Look at this function, e to the j beta sine omega t. Beta is a constant. This is the frequency, okay, like 2 pi FM. So the reason I have M here, you can probably understand this is the frequency of the message signal. FM is the, F sub M is the frequency of the message signal. So we will encounter this function and we have to find the Fourier series of this. Okay, finding the Fourier series is already complicated. We know the Fourier series of like basic functions, but this is exponential j beta sine omega. So let's pause a while, and we know if you write e to the j theta using Euler's formula, e to the j theta is cos theta plus j sine theta. In other words, e to the j theta is periodic. Okay, so e to the g anything is periodic, but then inside theta we are adding another thing that is periodic, sine. Sine has periodic. So this is like a periodic function inside a periodic function. This is really complicated, and we want to calculate the Fourier series of this. But at least we know it has a period, because this has a period, e to the this has a period, so there must be a period. So this is a periodic function, which means we go to Fourier series, not Fourier function, sorry, Fourier transform. We go to Fourier series, and we are interested in exponential Fourier series. Okay, so it turns out when we write this function as the exponential Fourier series, you may remember this from second lecture or from signals and system. In exponential Fourier series, here we write e to the j 2 pi f sub m nt, but here I have shortened to omega m. So these are the basis vectors in the exponential Fourier series, and c sub n are the exponential Fourier coefficients. So remember, trigonometric Fourier series goes like a0 plus a1 plus a2 a3 and so on, and then b1 plus b2 plus b3. But exponential Fourier series is like basically c negative 100, c negative 99, c0, c1, c2 and so on. We write in one summation. These are the Fourier, exponential Fourier coefficient. It turns out if we were to write this as an exponential Fourier series, the exponential Fourier coefficients are nothing but Bessel's functions, these functions, this guy. Okay, so basically, to summarize, when we try to calculate the bandwidth of tone modulated FM, we will encounter this function, and we may wish to find the Fourier series of this exponential Fourier series, and the answer is we are not going to derive it. The exponential Fourier series coefficients are simply just Bessel's function of the first kind. So instead of looking at the Fourier transform table, we look at the Bessel's functions table. Okay, and don't worry about this. I will do plenty of examples. I just want to give you a heads up about this, and also it would be nice if you guys can kind of go over this before the second lecture after the FM. Okay, now just to give you what is going on here, I have an example. So this is, I'm not even going to FM, I'm just explaining this part. Can you write e to the j sine 5t as an exponential Fourier series? So if you look at this, this beta, you don't even have to worry about this fundamental 5 radian seconds and so on. uh, beta is 5. Okay, we need some explanation here where the beta came from. Okay, if it is how do you say fundamental frequency is 5 radians per second? Yeah, it's here. 5, not radian, not hertz, it's radian per second. But actually all of this is not important for you. So all you need is beta is 1, and what else? You have to go plug 5 for this, and so it looks like this, and then you have to calculate jn1. Okay, that's it. So what is important is only beta. You can basically ignore this 5 doesn't go to the table, and don't worry about that. And then so you have to find c0, c1 and c2, and then to find c negative and c negative to c negative 3, we use this relationship. J negative 1 beta is negative 1 to the n, this. And then here is I looked up these values from the table. You know what, I'm going to tell you to ignore exercise 1, because when we actually calculate the FM bandwidth, we are not going to take this path. Here I was a little bit over eager. I was too eager to explain mathematically what is going on. So please just ignore exercise 1. It's far too complicated. Let's forget about that. Okay. So when we calculate the FM bandwidth, I will tell you how to use the table. Alright guys. So that's it. So everything here except exercise 1, and ignore the proofs. Please review this before the second lecture after the midterm. Okay guys. That's it.